It's pretty amazing when you think about it. Doctors can see right inside our bodies in real time without a single incision. The secret? It's ultrasound, and it's all powered by some really fascinating physics. So today, we're going to peel back the curtain and break down exactly how simple sound waves, stuff we can't even hear, create those incredibly detailed medical images we see all the time.
All right, so let's get right to the heart of it. This is the big question, isn't it? How on earth does sound create a picture? I mean, it really does seem like magic, but I promise you it's not. It's all based on a few core principles, and by the end of this, you're gonna get it. You'll see exactly how it all clicks into place.
So to really wrap our heads around this, we've got to start at square one. I'm talking about the most basic, fundamental property of a sound wave, and that is its strength. This is our first and maybe most important building block.
Right, so that first building block is called amplitude. Don't let the technical term throw you off. It's really just a fancy way of saying the wave's strength. And you'll see in a minute why this one concept is absolutely key to controlling how the final image actually looks.
Okay, the easiest way to picture this is to imagine a wave drawn out on a graph, right? The amplitude is just how tall that wave is, how high it goes from that center line up to its peak. It's really just the height of the wave. Yeah, the technical definition is maximum variation from its baseline, but honestly, just thinking wave height is going to get you 99% of the way there. So here's the takeaway, the thing you really need to remember. Amplitude equals strength. And here's the clinical payoff. When an echo comes back to the machine, the bigger its amplitude, the brighter the dot it's going to make on the screen. It's that simple. More strength means more brightness. It's a direct one-to-one relationship.
Okay, so we've got strength, which is amplitude. Now let's talk about power, and that brings us to our next big idea, intensity. Now listen, these two are definitely related, but, and this is super important, they are not the same thing. And understanding the difference is critical, especially when you start thinking about patient safety.
Intensity is all about concentration. Here's a great way to think about it. Imagine using a magnifying glass on a sunny day. The sun's power is spread out all over, right? But when you use that lens to focus all that energy into one tiny little dot, that's when things get hot enough to start a fire. That's intensity. It's the same idea with sound. It's the amount of power packed into a certain area. And here's the simple formula that explains it all. Intensity is just the power divided by the area. What that means is you can have the exact same amount of power. But if you squeeze it, if you focus it into a much smaller area, whoa, the intensity just skyrockets. And that's where things like tissue heating start to become a real consideration.
Okay, so we have amplitude, the wave's strength, and we have intensity, its concentrated power. So how do they actually connect? You might think, well, if I double one, the other one doubles too, right? A nice simple relationship? But nope, it's not that simple at all. There's a special mathematical link between them, and it has some pretty huge implications.
And here it is. Intensity is proportional to amplitude, squared. That little 2 changes everything. This isn't a straight line, one-to-one kind of deal. It's an exponential relationship. It means that when you make a small change to the amplitude, you get a way bigger change in the intensity. Let me show you what I mean with an example.
This makes it super clear. Let's say your amplitude is 2. Well, the intensity is proportional to 2 squared, which is 4. Simple enough. But now let's just double the amplitude. Let's kick it up to 4. You might think the intensity would double to 8, right? Wrong. The intensity is now proportional to 4 squared, which is 16. So by doubling the amplitude, you've actually quadrupled the intensity. That's the power of squaring.
Okay, so we've got a handle on the wave's strength and its power. But for any of this to matter, that wave has to actually travel through things, right? Through our body's tissues. And here's the thing, not all tissue is created equal. That brings us to our next big concept, acoustic impedance. Think of it like a bouncer or a gatekeeper at the border between different tissues, deciding how much sound gets in and how much gets bounced back. So what is this acoustic impedance? Well, scientists call it Z. And it's basically a unique property of every single material in your body. It comes from multiplying a tissue's density by how fast sound travels through it. But you don't need to memorize the formula. The best way to think of it is like an acoustic fingerprint. Every tissue, fat, muscle, bone, liver, they all have their own unique fingerprint.
And take a look at this table. You can see just how different those fingerprints are. I mean, look at the extremes. Air is way down there, almost 0. And bone is way up at the other end, almost 8. That's a massive difference. But then look at the soft tissues in the middle. Fat, water, liver, muscle. They're all kind of clustered together, right? All in the same ballpark. These differences, both the huge ones and the tiny ones, are the key to this whole thing.
So why do we care so much about these different impedance values? Well, because the difference between them is what creates the echoes. That's it. If everything in the body had the same impedance, the sound would just travel straight through and we'd get nothing, no image. It's the boundaries, the borders between tissues that create reflections. And that brings us to the final piece of our puzzle. So picture this. A sound wave is traveling along, happy as can be, and then bam, it hits a boundary. It's going from, say, liver to kidney. What happens? Well, two things. Part of that wave is going to keep going, pushing deeper, but another part of it is going to bounce back, like an echo in a canyon. And that echo, that's the part we're listening for. That's the signal that builds our image.
And this right here, this is the golden rule of ultrasound. If there's one thing you take away about how images are formed, it's this. The bigger the difference, the bigger the mismatch in impedance between two tissues, the stronger the echo that bounces back. It's that straightforward. A tiny difference gives you a weak little echo. A huge difference gives you a massive, screaming echo.
All right, let's make this real. Let's do a little case study. Imagine a sound wave traveling from a fluid, like an cyst, into the liver. Now, if you remember that chart, their impedance values are pretty close, right? 1.48 and 1.65. So what's your guess? When the wave hits that boundary, are we going to get a big, strong echo or a little faint one?
Turns out it's a pretty weak one. Only about 5% of that sound wave actually reflects back. We call this good acoustic matching. Because the tissues are so similar, most of the sound, a whopping 95% of it, just keeps on going, deeper into the liver. And that's fantastic. That's what we want. It allows us to see structures way down deep. If everything bounced back at the first boundary, we'd never get a picture of anything further in.
Okay, now for the total opposite scenario. Case study number 2. What happens when that sound wave tries to go from skin and muscle, which has an impedance around 1.7, and to air? You remember air's impedance, right? It's basically 0. We're talking about a massive mismatch here. The Grand Canyon of impedance differences.
So what happens? A wall. Almost 99% of the sound wave smacks into that air and reflects right back. Nothing gets through. This is what we call terrible acoustic matching. And this one single fact explains why we slather that cold gel all over you for an ultrasound. That gel's only job is to get rid of that tiny, invisible layer of air between the probe and your skin. Without it, you'd get no image at all.
All right, let's take a breath and connect the dots. We've covered a lot of ground here, right? We started with the basic strength of a wave, then its concentrated power, then we talked about the unique acoustic fingerprint of different tissues, and finally, how the boundaries between them create the echoes that make everything possible. So now let's bring it all home and see why this stuff actually matters in the real world. Here's the cheat sheet. When a sonographer is fiddling with the knobs to make the picture brighter or darker, they're literally changing the amplitude. When doctors talk about patient safety, about not heating up tissue, what they're really concerned about is the intensity. Every single dot you see on that screen, how bright or dark it is all thanks to the impedance mismatch that created it. And of course, that whole thing with the air, that's why that ultrasound gel is an absolute must-have. So think about what we've done. We followed the journey of a single sound wave and figured out how a single echo was made. But here's the kicker. An ultrasound image isn't just one echo, it's built from millions of them. So that leaves us with one last big question. How does the machine possibly listen to millions of these echoes, all coming back at different times with different strengths, and weave them together into that incredible, moving live picture we see on the screen? Now that's where the real magic happens.